And it's already time to introduce the last keynote speaker of the day, Professor Xiaoxiang Zhu, who is a professor of data observation at Technical University Munich. And she will talk about AI for Earth observation and social good. Xiaoxiang, the floor is yours.
Hello, everyone. It's actually very convenient to be the last speaker of the day because many things has been introduced. I can directly jump onto the point, right? So, the talk is about AI4EO, but we emphasize a bit on the social good aspect. Start with figure. You all know we have petabytes, tens of petabytes of data. However, what I want to show with this graph is on the right, you see the amount of labeled data in the field because we are talking about AI, right? And the numbers we can get is basically, although we have several hundreds of petabytes of data free and open, if you look at the labeled data, it's actually still around 0.2 petabyte. So we have less than 1% of the data where we actually have labels. And also to look at a little bit, when we started back then, there were nearly no benchmark data sets available for deep learning. Things has changed, of course, a lot in the past decade. If you look at the evolution of the benchmark data sets that are made available to the community, you will see bubble size is the size of the data is getting bigger. And also from the type of tasks, you will see starting from the simpler type of tasks like classification, object detection, we are now more reaching to the core problem of EO, which is regression. We try to derive geophysical parameters from the data, and etc. So being a bit services to the community funded by the DIS Space Agency, we have been developing a platform, it's called EarthNet, where what we are trying to do is to put together all the benchmark data sets in the field of AI4EO. We also provide deep learning models, libraries, attributes of the data sets. So if you are expert or you are just entering the field, I hope our platform can offer you something. Also, since we are talking about libraries as well, maybe not known to many of you, actually my team, we are the main developer now for the TouchGeo library. We're now working on the time series functionality, which will be released in the next month, in case you're interested. Okay. So we have heard about satellites from many of the talks. From Irena, you also see a whole bunch of applications we're supporting. Where we do as AI and data science is rather in between. We work on information retrieval, try to turn these petabytes of data to insights. And of course, in order to master the whole topic, today we're very much focused on machine learning, but it's also important to highlight other domains which are important, like the more model-based signal processing methods. And the last point, whenever we talk about really large-scale applications, I think nowadays we have to deal with big data. Therefore, big data analytics and HPC are also gaining, let's say, significance in the field. Now, come to the topic of today. When we talk about social good, what can AI4EO offer? I would first starting with some, let's say, motivating examples. The first example is related to urbanization. I think known to everybody that we are living in an urban planet. If we look at the geographic distribution of urbanization, you will see that they are mostly happening at the moment at the developing areas. And of course, to help the urbanization be more, let's say, planned, the first-hand information we need is more or less the geo-information of the current status quo. Everybody asks questions. I also ask a question to the audience. Do you know how many buildings do we have on the Earth? Please make a guess. 1 billion. Any? 10 billion. Okay, yeah, it's easy for you to guess, but it took me 10 years to answer this question, okay? Let's start with some official data. From the UN, they don't count buildings, but they estimate, right? They say there are 4.1 billion buildings on the Earth. Let's take this number as it is for now, but I will tell you it's not the truth. And if you talk about open data for urban research, everybody talk about OpenStreetMap. For a city like Munich, where I'm based, or Zurich, of course you have everything. But if you look at the global picture, building footprints, the very basic information, right? There are only 600 million buildings have building footprints in OSM, which is less than 15%. If we go to the height, then it's even worse. So the less than 1% of these buildings actually have height information, and the error bar is actually very big. So we want to close this gap. As I already said, it took us 10 years to present the approach. There are a lot of pitfalls in between, but now I'll only present you the success story. Of course, the first thing you need to do, you need to choose the kind of data that are possible for us to get individual buildings. Unfortunately, the Sentinel class is a bit too coarse. If we go to the master solution, that would be really expensive. In the end, we went for a compromise. The Planet data, which is the new space approach which has been introduced. It has 3 to 5 meter resolution. And this is a kind of overview of the whole method. There's a lot of things behind this one graph. I can talk for hours. But in the end, of course, we have the data acquisition part to fill out interesting data. Then there is a branch where we try to estimate the polygons from the planet imagery. And another track, we basically inspire from the RGBD kind of development in the computer vision community. We try to estimate building height from the molecular planet satellite imagery. And of course, once the building polygons and the height are available, it makes no sense that we ignore what has been already made publicly available through different kind of platforms, OpenStreetMap, Google, Microsoft. Then in the final stage, we bring everything we could find in community to fuse the best possible quality of global building polygons and fused together with the height we derive. In the end, we get what I can present today. Okay, before I go to the results, maybe just to highlight one of the blocks, like the building height estimation. So what we did is we, of course, built up training data sets from 161 cities sampled across the globe. They are paired satellite data with the building heights. And of course, we need to develop a tailored deep learning model for that purpose, because this is per se a year-post problem. And also we have the problem that the height of the buildings actually follow a long tail distribution, because there are way more buildings which are lower than the skyscrapers. And of course, we also need to constrain the errors. If we talk about regression, then the errors can go crazy if you don't do any kind of regularization. These are the challenges we tackle with this model. And now I present you the final results. So in the end, we processed about 800,000 planet imagery across the globe. The color indicates the data quality. And actually, a few weeks ago, I'm very proud, we released the Global Building Atlas datasets. This is open, global, and finally complete datasets of the building polygons, building height, then combined is the level of detail 1 3D model. And we released the code, the data. We also provided a web view for everybody to have a quick look at the data. Here is the moment I can answer the question. In the end, across the globe, we have 2.8 billion buildings. It's not 4.1. And what you see in the middle is the building volume distribution across the globe. On top, you see all these kind of nice statistics, like the number of buildings, building areas, distribution across continents. What is very interesting is the fourth one, which is the building height IMSE. So you will see, depending on which continent we're talking about, basically the height error of buildings is from 1.5 meter to 8.9 meters. And the left and the right, you see these kind of samples, the height mesh maps, and finally the LD1 models. And of course, we have this information now everywhere. You can go to any cities, you will be able to see detailed models. And we provide this web view. Basically, you can also scan and explore by yourself. If you go to the web view, you will land in Munich, where we base. But basically, you can zoom into every building to see the building heights. And you can zoom out. This is the building volume map at a coarse resolution. And then you can basically go to any city of your interest. In this case, for example, if we go to Bangkok, so if you zoom into the certain level of detail, you will be able to see the global LD1 model. You can lay out with different type of background layers. And of course, you can also search, give a city that you are interested, and you will be navigate to the city, in this case, Sydney. And also we have here a drop-down menu that you can select some example city to see. Okay, so you may wonder, why do I care how many buildings are on the planet, right? So you can do a lot of analysis with this, of course. One question is, due to the war, there are a lot of discussions about alternative energies. Of course, solar energy is one of the major alternatives which are under discussion. Then we were asking ourselves, if now we have the funding to place solar panels with the affordable price on the rooftop of every building, can we actually then be able to cope with the global energy challenge? So this can be easily done. You can put the global building layer we have along with the Solar Atlas open database. Then you are able to calculate the solar potential of every building. And if you put them together, you basically can get conclusions that it is indeed possible 1 to 3 times. And this is the record of 2020, because this is the energy peak of human history. Afterwards, because of COVID, it went down. And today we also talked about sustainable development goals, like zero poverty. You know that in order to monitor their progress, we need some indicators, right? So far, for example, for some of these indicators, we are still evaluating based on the building areas per capita. This is per se biased, because you can never compare high-quality apartment buildings to lightweight slums. The really more unbiased measure would be building volume per capita. This would be the real space per person would really have, right? So we implemented these ideas by computing the GDP per capita, try to correlate with the building volume per capita. On the right is the building area per capita. Indeed, you will see there is a huge boost of the correlation coefficients, which says this is a way more reliable indicator. And also, we can do a building volume versus population across all countries. Immediately, you see the global inequality problem. On the left, you see the countries which has the biggest building volume per capita, and this is the lower tier of the whole thing. So you get a very good picture globally. That was the first example. The second example is rather related to climate change. You all know that glaciers, they are very important climate variable, and it's very important to do the monitoring. What we have done in this domain is, in this work, we are using Sentinel-1 data, and we try to detect the coastline through the machine learning model. if you treat it as, let's say, interesting scientific problems, we can, of course, develop tailored methods for that. In this case, we are considering this task to be a dual task problem. One is to detect the edge, the other one is to the segmentation. And also because the glacier coastlines, they have different dynamics, it's important that we have a hierarchical attention mechanism to take this into account. And in the end, you will be able to get a very nice results. But this is not yet, let's say, relevant for real-world application. Because if we talk about glacial calving front, it's not useful at all if you just look data from one sensor at one time point. Instead, we need to put data at least for 3 decades, then we can talk about climate. In this particular case, we are looking data from the past 40 years. This means we are looking at the data across different kind of sensors. And of course, there's a lot of generalization, transferability issues that we need to handle. And we also need to do a lot of let's say, modification to the whole pipeline. But in the end, we have done this for the whole Svalbard. In the end, we come up with 125,000 of glacier calving front from the past 40 years. Based on this type of data, then finally we're able to draw statements, right? So for example, we're able to quantify the calving front change rate as shown on the left. On the right, we will be able to classify is this glacier advancing, retreating, is or rather a surging glacier. And also you can get a correlation with environmental factors. Everybody suspected air temperature is the driver, but in the end you see ocean temperature are the stronger driver than the air temperature. And also on the right, we are able to finally quantify seasonality, for example, from the data. Okay, these are the 2 examples, very brief ones, but at the TU, we're doing much more. I don't have time to go to this detail, but I want to pinpoint a few points. We look a lot on natural hazards with particular focus on flood droughts and the landslide and the volcanic deformations, if you're interested. The green layer, we do a lot with forests and crops. I made a deal with Davis. I don't talk too much about ecology, but nevertheless, I mentioned one data set which could be interesting here. It's called Global Geotree. Basically, we had 6 million tree occurrence paired with Sentinel-2 time series across about 20,000 species. And this data is available for everybody. And also we have a model, it's called Geotree Clip, which can do this kind of tree species classification. We are more from the remote sensing AI side. We are always looking for interesting collaborations, more answering ecological questions based on this type of data. And another thing is, for example, we have actually a very big team working on AI4EO to support climate science. Okay, now I have shown you motivating examples, and today it's a lot about actually act, from data to act. To just give you a bit impression, what is happening actually in this broad AI4EO community, I did a very simple exercise. So by simply looking at the Scopus, try to figure out AI4EO literatures, which is read, how it evolves. You see that we have now more than 10,000 papers per year on this topic. But now if we add the policy angle, on top of the keywords on top, you will see we are going to a much lower bars. This means we still need more awareness actually in the community, not only try to produce visual opinion results, but really think about what we can do with that. And of course, besides the awareness, there is also a lot of challenges still in the domain, which made the AI-derived results not yet so trustworthy. And here is just an incomplete list of these challenges, and also it's a summary of the methodologic questions my team is working on. So these are the open issues. So how to bring physics domain expertise bias back to the combined with the data-driven paradigm, also very nicely highlighted by Elena. For those of you interested, we actually last month released a platform called Hydro PML, where we try to at least offer a platform to do this for the hydrological domain. Another topic is reasoning. So far, get a satellite image, try to understand what is on it. That's easy, but really try to do a higher level, let's say, reasoning. So from the spatial temporal relations to derive a certain higher level knowledge, this is not yet there. So one example is the permafrost that you cannot detect. You need to derive it from the disturbances. Of course, then in this case, you need a spatial temporal relation. Another domain is more human-centric part. This is what we call reasoning. But another thing is generalizability, transferability, which has already been very well highlighted by Mark, I think, that we have data-rich areas, but we're interested in data-scale areas. We have labels for previous sensors, but we are looking for future sensors, these kind of things. And another topic is uncertainty quantification. Being an Earth observation scientist, getting any results without an error bar has no meaning. So you really need to look at uncertainties in the data, in the model. We should be able to give alarming signals if there's out of distribution. Explainability, I don't think I need to go to detail, but also foundation models, which has been talked a lot. What I see the big promise there is that we learn general representations from this huge data archive we have, such that we're able to do downstreams with much less labels, with way less carbon footprint. But I will come to this point later. But also other things. Last point, probably I should also say a few words about this. Ethics, when we studied this topic 5-6 years ago, we're making a lot of large-scale data available to the community without understanding the ethical issues behind that. So there are, of course, high-level ethical guidance from the EU, but as a technical person, we don't understand. Then we had actually a lawyer, her name is Nalini, working with us in the lab day-to-day basis for 5 years. So we are trying to figure out from a bottom-up approach, how could we do actually ethical accompanying research? There's also papers about that you're invited to read. It's not so technical when you really want to change your mind to read something else. Okay, so I will not go to details of all this, of course, but today, nevertheless, I want to use the opportunity to talk a little bit about foundation models, because you basically hear them from every talk. So in our understanding, if we are really talking about Earth and the climate foundation model, given that we only have one Earth, what is very much ecology in the community is that we have hundreds of petabytes of multisensory data. We should learn representations to support all different types of downstreams. This is basically the definition of a foundation model. But I want to highlight that there's a few things that we should actually pay particular attention to. So firstly, we need to ensure the physical consistency of this kind of data-driven type of knowledge. And another thing is we are talking about EO, weather and the climate of the same Earth. There should be one holistic model have all these components in. But since EO, weather and the climate, we're addressing completely different spatial temporal scales. So probably realistic framework is more like a geographic mixture of experts that we have EO, weather and climate component, but they should be able to talk with each other. That's the foundation model itself. On top of that, this model should be able to communicate with the classical physical-based Earth system models on the one hand, and on the other hand, being able to profit from the general purpose large language model, which is our human wisdom, right? So that would be my idea of how an ideal Earth and foundation model could look like. I don't need to go to this one anymore. Everybody know why we're doing that. And when we started foundation model research back then, it's not yet called foundation models. So we have been releasing pre-training data sets for the purpose. We were developing tailored foundation model with a focus on the multimodality and also the language integration. We were producing benchmarks to test different foundation models. I have no time to go to all of these, but I will talk about two very recent work from the lab. The first one is Copernicus foundation model, because we heard so much about the very exciting Copernicus program. So what we have done is we built up a Copernicus pre-trained model consists of 18.7 million images from all Sentinel missions, from Sentinel-1 to Sentinel-5P plus DEMs. On top of that, based on the DOFA backbone our lab developed a few years ago, we extended that to also include metadata like time, location, sensor specifications. This is called a Copernicus foundation model. And finally, we provided a comprehensive benchmark go beyond only the Earth observation part with high-resolution data, but really also go to air quality, biomass, and many other tasks that bridge EO, weather and climate. This work is accepted at ICCV. That's not the first ICCV paper we have, but in this one, particularly, we are proud we get full score from every review. So stay tuned. Another thing, the second work I want to highlight is called DOFA CLIP. For anyone who is working on VRMs, particularly in the EO domain, you all know that the biggest challenge we have is we don't have very well aligned image features and the text features. Not talking about multisensory. So we try to close this gap. So what we have done is we released 2 million image text datasets covering 6 different modality, multispectral, SAR, hyperspectral, elevation maps, infrared imagery, area imagery. And you then wonder how we align the features. The trick we do is, since we all align them with language, we are using language as a reference to align all other modalities. So this is the basic principle of DOFA CLIP, and you may wonder what we can do with this kind of VRMs. It's just fancy, but that's not true. This is a demo. What we are doing is we choose any kind of data, randomly selected kind of data, and as a human, we try to describe this image to the best of our knowledge. And then you run through from this vision language embedding, you will see the model will be automatically being able to figure out what is the correct description of that image. So this really means we will be able to semantically search the Earth cross multimodality with zero shot, meaning the model does not need to see any example. If you enter a house with backyard, it will give you where it is. Okay, so that's the 2 examples from our recent work. But if you look at the involvement of the whole EO foundation model community, so you will really see we have a foundation model rise. We don't yet know where is the peak, right? And if you look at all the details of this model, this is the tree. And of course, this is branches are contrastive models, generative models, or hybrid ones. As a university group, we are very happy being able to contribute to these. But the key message I want to discuss with all of you is that we already have 130 foundation models. Foundation models is supposed to be foundational. Do we need yet another 500 foundation models, right? So this was the development we observed in the beginning of last year. Then finally we decided that we step back to really think what kind of features are really important if we just have the chance to building one foundation model for all. So through this exercise, we come up with a list. So we said to ourselves, we don't need the buzzword. We really need to know what is necessary if we have a Earth foundation model that are helpful for everyone who is doing Earth-related research. So there are 8 must-have features. Geolocation embedding, which is very much discussed before by Mark, set clip. We need, in a foundation model, it's not only the model and the way of training it, but also the ways. This comes from the pre-training data sets. So we need to have a very balanced geographic representation. And it should be scale awareness. Actually, it doesn't matter which kind of resolution of data we put in. It should be automatically being able to relate to any kind of characteristic size in the physical world, like the building floors is typically 3 meters, something like that, right? Then it should have wavelengths embedding, meaning that I don't care how many bands my sensor actually has. It should be automatically able to embed this. Another thing is the time variable. That's, of course, I don't need to motivate this because we now anyway have time series of the Earth, so to say. And then it should be able to work across different sensors, given that we have so many, very, very soon, 5,000 satellites there to take imagery, right? And of course, per se, it should be task agnostic. And the main purpose of doing this is not only to boost performance, also to minimize the carbon footprint. That's the must-have features. If there's a model don't have these, for me, it's not yet really a foundation model for the Earth. But there are also really higher desirable features. So uncertainty quantification. If there's a foundation model, we get an embedding. But do you know how reliable is this embedding? Do you know whether your data is actually out of the distribution of that model? We did an uncertainty score there, so the variance. And then physical consistency, that's the only way we're able to bring this together with the Earth system models, with the physical world. And last but not least, integrating knowledge of large language models, vision language models, which is the past 5,000 years of human wisdom. So these are, in our opinion, the real essential features. If we only have the chance to build one foundation model, here is where we should head to. And where we are, right? I talked about Copernicus foundation model, DOFA CLIP. Today you heard about TerraMind, Alpha Earth. DOFA was also our model. You will see that we're actually only covering several of these must-have features. So we're really far from ideal foundation model. And of course, another message is if you look at the spatial domain modality and so on, we still see there is a gap between the EO and the climate foundation model. With the companion foundation model, by doing this embedding, we are trying to bridge, but there are way more effort needed actually in this domain. So, Alpha Earth, everybody was talking about that. Firstly, I think we should really acknowledge big tech companies like Google really run through hundreds of petabytes of data through the foundation model, provide this kind of embedding to the community, such that you don't have to deal with raw data, you can deal with the embeddings, right? But we are not yet there to have the idea embedding. So my last message is that let's really think about how an idea foundation model should look like. We should have an agenda that we try to work on the rather more challenging part of the whole thing, to build in uncertainty, to get the physics inside, and try to integrate with large language models. Once this model is there, I think the big tech companies like Google or the agencies, European Commission, European Space Agency, they will be happy probably to produce the embeddings along with the data sets, which is probably way more expensive than these embeddings. Okay, so this closes my talk. A few statements. So I hope with the motivating example, I show you that there is indeed an invaluable value there by combining AI and big AO data. And on a more kind of a group perspective, release this global building atlas data sets. By the way, the data is released under non-commercial license. There are a lot of companies contacting us about commercial usage. We're still working on that. But for academic, everybody can use it already now. Then, really towards along the road from data to insight, we're not yet there. There are a lot of open issues, uncertainty, explainability, transferability, you name it. So we really need joint force there. And last but not least, Earth and Sky foundation models. Is there a promise? Yes, there's enormous potential, but we are really stretching the surface, and we need to align the effort a bit better that we really tackle the hard problems, so to say. Okay, that's all, and then here is my contact. Thank you.
Thank you so much, Xiaoxiang, for this very engaging talk. I think we had a lot of very powerful key messages. So after that, are there some questions or reactions? Yeah, don't be shy.
So just, first of all, thank you for the talk. It was super interesting, all of the topics. Just to come back to the very beginning, to the building mapping. So one thing with buildings is that we're still building buildings every so often. Mm-hmm. Is this something that's in the scope of your work to also assess what construction is being done, where and how doable is that? Because I guess there has to be a lot of computing cost and perhaps also satellite imagery costs since you're using Planet. So how doable is that? Is that something you're aiming to do?
Yeah. Okay, so the reason why we selected Planet data is also because the price is affordable. First of all, for those who are interested in update by themselves, our model are open. On the other hand, my lab, we are planning doing these updates. We're actually working on a time series of the building models, but of course, we probably can only bring it to a certain stage we are wishing, then the community will take over.
Are there other questions? Okay, so I have one question about your view on foundation models. And I completely agree that not everyone should design a new foundation model. And probably it's also a problem of the terminology that, okay, maybe we need a better definition. But apart from this question of the definition, how do you align having one idea of a foundation model and waiting for something big to take care of really the implementation and the idea that science is not a straight line, and maybe we also need to explore a lot of new different things that can come from many different teams, so that we know, okay, which approaches can be the most successful.
Yeah. So I fully agree. So there will definitely joint forces needed from the community to bring the methodology to a certain level that we can basically create such a kind of idea foundation model. What I'm basically advocating is probably going beyond just producing quickly yet another foundation model. Look at the metrics we provided, look at where we actually need effort, and then try to focus on these problems. And in the end, it will take 2-3 years of development that we are able to cover various aspects. Then this would be the time point that we probably, as a group of the community, try to bring one idea model that can cover this feature to the stakeholders who actually have the computing power, data access to do the embedding. So that's basically the approach I'm trying to somehow promote here.
Thank you for this inspiring view. If there is no other hot question, let's thanks again Xiaoxiang and both our speakers from this last keynote session.
Thank you.